In this module, we are going to be continuing our discussion of postulate 3 of quantum mechanics, the measurement postulate as it is so called. And we're going to bring out certain important aspects of this postulate, specifically as it pertains to measurement. The chief goal of this module is to try and tell you the difference between a statistical mixture and what is called a linear superposition. So remember that in the last lecture, we wrote down states such that psi is some linear combination of other states like A1 phi 1 plus A2 phi 2, right? So we said that this is psi is a wave function that is a linear combination of the other wave functions phi 1 and phi 2. So in general, if phi 1 and phi 2 are acceptable states of the system, then any linear combination of them is also an acceptable state of the system. Okay, so this is called linear superposition, and it's a very important principle in quantum mechanics. It's what makes a theory linear. So I want to distinguish between this quantum mechanical linear superposition of states with a classical notion of statistical mixture. What is a classical statistical mixture? So let us look at a very simple example. So let us say that I have a box, okay, some kind of a cylinder. And in this cylinder, I have a bunch of blue balls, and a bunch of red balls, right? Right. So there is a certain number of blue balls NB and a certain number of red balls NR. And if I pick a ball at random, then the chance that I will get a blue ball is, of course, NB over NB plus NR, right? So this is the probability of blue. Similarly, the probability of red is NR over NB plus NR. So this is a mixture of two different kinds of particles. So this is we call this a statistical mixture of two different kinds of particles. So I want to distinguish between this classical statistical mixture of two different kinds of particles and the quantum mechanical notion of linear superposition of two states. Okay, so I want to basically point out that this this guy is distinct from the classical statistical mixture of particles. So let us try and elucidate this by means of a hypothetical experiment. Actually, a real version of the experiment that I'm going to be actually describing has been actually performed, and this is called the Stern-Gerlach experiment. Okay, this uses the notion of electron spin, but since we have not defined such quantities in this course, I'm going to be simply using a sort of a simpler version of the same experiment to try and illustrate the distinction between a linear superposition and a statistical mixture of two particles. Historically, this was a very, very important experiment because it sort of placed quantum mechanics on a firm pedestal. Okay. So to begin our discussion of our version of Stern-Gerlach experiment, assume that there are two observables. Let's call these observables A and B. And in quantum mechanics, they are represented by two Hermitian operators, A and B. Okay. And let us assume that A has two eigenvalues and two eigenvectors. Let's call these psi plus with eigenvalue A plus. And psi has another eigenfunction psi minus, which has eigenvalue A minus. Then there is a second observable B, and B has two eigenvectors, phi plus, which has eigenvalue B plus, and another eigenfunction phi minus that has eigenvalue B minus. Okay, so you can think of these as 2 by 2 matrices if you so wish. but it really doesn't matter. Okay, so we are trying to measure A or B, but we will do this in a very peculiar or very proper sequence. So to do this, to start this experiment, assume that we have two machines. Okay, we have two machines. Let's call these machines M1 and M2. We don't care about what is going on inside these machines. All we care about is the fact that the machines M1 and M2 are sensitive to the eigenvalues of A and eigenvalues of B respectively. This means that if I feed a beam of particles, let us say, okay, so if I feed a beam of particles to the machine, let us say M1, then this machine splits out two beams. Okay, so if this is the machine M1 and I feed into it some stream of particles, and it splits this stream of particles into two streams, one that has eigenvalue A plus and one that has eigenvalue A minus. Okay, what this means is that if I measure A on the first stream of particles, I get eigenvalue A plus, and if I measure A on the second stream of particles, I get the value A minus. So M1 is a machine that is designed to do this. Okay, so similarly, if I feed a stream of particles into the machine M2, M2 splits out two beams of particles. Okay, this is M2, and M2 splits this according to the values of the B observable. So M2 gives me two beams, one with eigenvalue B plus and one with eigenvalue B minus. So let us assume that people have constructed these two machines, and let's just take them for granted. Now we will try to use these two machines to point out what is a fundamentally quantum mechanical concept when it comes to experiments and measurement. Okay, all right. So as a step 0, let us do whatever we just did. So step 0, the first step of our experimentation is to simply take some stream of particles and feed it into the M1 machine. And the M1 machine gives us two beams. Okay, so the M1 gives us A plus and A minus. And this is what the M1 machine was designed to do. So this stream of particles, let me call it some initial states phi. Okay, all right. So there is nothing surprising here, but let us move on to step 1. Step 1 is the following. So I take this stream of particles, feed it into M1, okay, and then I get two streams, A plus and A minus. Now what I will do is I will claim that I'm only interested in the A plus beam and I don't care about the A minus beam. So I'll put some kind of a blocker here. Okay, I'll put some kind of a blocker that blocks this A minus beam. So I don't want any A minus beam, and I only want the A plus beam. Okay, now so this is my machine M1, of course. Okay. So in this A plus beam that is coming out here, okay, in the path of this A plus stream of particles, this is a stream of particles upon which if I measure the A observable, I get the value A plus. In the path of this A plus beam, I will put the machine M2. Okay. Now what happens? I will get two streams of particles. I'll get one stream here and one stream here. And these two streams of particles will have some B plus and some B minus eigenvalues. What does this mean? Well, you might be able to explain up till this qualitatively, sort of in a statistical mixture interpretation as well. So this is how I will explain it. So I will explain it like a classical physicist might try to explain it by saying that, look, the initial phi beam is composed of, I don't know, two different kinds of particles, which has some proportion, some statistical mixture of A plus and A minus. And you're blocking out the A minus, that is fine, you're taking the A plus. And then he or she can go on and argue that, look, the A plus beam itself may be a statistical mixture of B plus and B minus. So just like this box is a statistical mixture of red balls and blue balls, the A plus beam is a statistical mixture of particles which would have an eigenvalue B plus for the B operator and particles that will have an eigenvalue of B minus for the B operator. Of course, we won't be able to explain the quantitative results of experiments this way, but at least qualitatively, you might get away with this kind of an explanation, right? So it seems like both a quantum mechanical superposition of states and a classical statistical mixture of particles can seem to explain up till now. All right, we will move on further. Step 2. I will do the entire experiment again. I'll have a stream of particles. Okay, I will feed this into the M1 machine. I'll have two different streams. I'll block the A minus stream. Okay, I'll block the A minus stream, and on the A plus stream, I will put the machine M2. Okay, and now I will get two different kinds of beams, B plus and B minus. Now I will again block the B minus beam. Okay, so this is my M1 machine, which gives me A plus and A minus, but I'm blocking out the A minus. On this A plus machine beam, I'm putting in the machine M2, which splits it into B plus and B minus, and now I'm blocking the B minus beam. So far, so good. Now, remember, statistical mixture guy tells you that the A plus beam is some kind of a statistical mixture of B plus and B minus. So the way we have structured this experiment is we have filtered out the A minus beam and now the B minus beam. Now, in the path of the B plus beam, I'm going to put the M1 machine again. Okay, and now we will ask the statistical mixture guy, what does he expect? Now he or she is sure to say that, look, if this is a mixture of red balls and blue balls, and if A minus are the blue balls, we've filtered out the blue balls already, right? So there should be no blue balls left. So if I put the machine M1 in the path of B plus, I should get only one beam out, which is only A plus, because A plus is the parent beam. Remember, all this experimentation starts only with the beam that has an eigenvalue of A plus when the A operator measures the is measured. So that's what he would say. So let's go ahead and do the experiment. So let's take the beam that has an eigenvalue of B plus for the B operator, and let's put the machine M1, whose job it is to split any beam into A plus beams and A minus beams and see what comes up. If you actually do this experiment in a lab, what you will find, rather surprisingly, is that it's not one beam with A plus that comes out, but rather two beams. One that has eigenvalue A plus for the A operator, one that has eigenvalue A minus for the A operator. In other words, if you put this machine, it will actually split it into two beams. And if you measure the observable A on the first beam, you are sure to get A plus. And if you measure the observable A on the second beam, you're sure to get A minus. So if I assume a statistical mixture interpretation, and if I assume that all the A minus has been blocked already, then I'm left in a very bizarre situation where I would have to explain how I generated this A minus beam. How? So there is no reason for the A minus beam to be there because I've blocked it out already, right? So a classical way of explaining this experiment, which was actually done with electron spins by Otto Stern-Gerlach, cannot explain the results of the experiment. Even if you filter out the A minus beam, you would still get the A minus beam later when you're trying to measure A. So now let us try to understand what is the quantum mechanical way to understand this experiment and how does the notion of linear superposition help us? Well, the way you would explain step 0 is very simple. You would simply say that phi is a linear superposition of, before you actually do the experiment, before you put the M1 in the path of phi, I would claim that phi is some linear superposition of A plus and A minus. Well, I can write it as an equal linear superposition. So I will write 1 over root 2 psi plus psi minus. Not a statistical mixture. I'm not claiming that this beam of particles is actually, so suppose if there is 10 particles in this beam, I'm not claiming that 5 particles is with A1 and A plus and 5 particles A minus. That is a statistical interpretation. What I'm claiming is that this beam can be written as a linear superposition of a beam with eigenfunction psi plus and a beam with eigenfunction psi minus, with, I'm choosing the relative weight of psi plus and psi minus to be the same. Okay. Now in step 2, when this A plus beam is split into B plus and B minus, I would have to explain how I generated A minus again. The way I would do that is, again, by claiming that whatever has happened, now that you have the B plus beam feeding into the M1 in the last stage, the B plus beam, of course, corresponds to the state phi plus, right? The B minus beam corresponds to the state phi minus. Why? Because if I measure B plus, it corresponds to phi plus. I'll explain this more clearly as we go along. So this B plus beam is actually the state phi plus, but the state phi plus should also be regarded, or can also be regarded, as a linear superposition of the states for psi plus and psi minus. Just like I can regard the initial beam as a linear superposition of psi plus and psi minus, I can also regard the phi plus beam as a linear superposition of psi plus and psi minus. And if phi plus is alpha times psi plus plus beta times psi minus, what should phi minus be? You can actually easily guess this, because phi plus and phi minus are the eigenfunctions of a Hermitian operator, so they have to be orthogonal to each other. So phi minus has to be equal to minus beta psi plus plus alpha psi minus. Why? Well, what is the dot product of phi plus dot phi minus? Phi plus dot phi minus has to, this is my shorthand notation. This actually means phi plus star of x, phi minus of x dx in the position space representation. Phi plus dot phi minus has to be equal to 0 because these two are orthogonal to each other. And since psi plus and psi minus are also orthogonal to each other, phi plus dot phi minus is basically, so multiply this and this together, you will get minus alpha beta psi plus dot psi plus minus beta square psi minus dot psi plus plus alpha square psi plus dot psi minus plus alpha beta psi minus dot psi minus. And since psi plus and psi minus are also eigenfunctions of a Hermitian operator and they're also orthogonal to each other, psi minus dot psi plus is 0. This term is 0, and psi plus dot psi plus is 1, and psi minus dot psi minus is 1. So this is minus alpha beta plus alpha beta. So this is also equal to 0. So if you construct it this way, then the eigenfunctions are properly orthogonal to each other. So you should regard the B plus B as a linear superposition of the states psi plus and psi minus. Also the B minus beam is also the orthogonal combination minus beta psi plus plus alpha psi minus. So looking at the state of a system as a linear superposition rather than a statistical mixture seems to explain the result of this experiment. How does it explain the result of this experiment? Well, now look, the beam that you are feeding into M1, the last stage, can be written as something times psi plus plus something times psi minus, right? Now psi plus is the eigenfunction of A with eigenvalue A plus, and psi minus is the eigenfunction of A with eigenvalue A minus. So it is obvious that if I measure A, I'm going to get A plus with a probability alpha square and A minus with a probability beta square. Okay, remember our discussion of probabilities and how to project out probabilities. The probability amplitude that I will get A plus from, if I measure A plus on this beam, is basically the projection of psi plus on phi plus, right? So this is basically alpha. Sorry, probability is the absolute square of the probability amplitude. So this is equal to alpha square. Similarly, the probability of getting A minus is beta square. So it really doesn't matter that we have filtered out the A minus beam in the initial stage. Why? Because at every stage prior to doing the experiment, we regard every beam as some kind of a linear superposition. Now, which kind of a linear superposition depends on what we want to measure. So suppose if I want to measure B, I will regard A plus as a linear superposition of B plus and B minus, and I will try to compute the probabilities. So the fact that I get two beams at the last stage is not a surprise to the quantum mechanical scientist, but it is a surprise to the classical scientist, because he thinks that they are like balls, red balls and blue balls, and one of them has already been filtered out. That is not the case. This is not a statistical mixture of particles, but each beam should be mapped onto a state of the physical system. And this state of the physical system can be written as a linear superposition of other states. Okay. So with this knowledge in mind, let us answer one other question that is also very important. Okay. What is the other question? So suppose if I prepare a system in some state psi. Okay, let us say I prepare a system in some state psi. Okay, all right, and now I want to measure some observable, let us say A. Right? So in other words, I want to say, if I measure A on this system, what would I get? Now let us say, just like before, let us say that A has two eigenvalues. A has two eigenvalues, A plus and A minus, right? Now, regardless of which physical system it is, if A only has two eigenvalues, quantum mechanics tells you that if you measure A on some system, you can only get one of the two eigenvalues, A plus or A minus. So before you do the experiment, you can figure out what is the probability of getting A plus and what is the probability of getting A minus by writing psi as some linear combination of the eigenfunctions of A, which is alpha times psi plus and beta times psi minus. It's different, so you can put some alpha tilde and beta tilde to contrast with the previous linear combination. So let us say that I measure A, okay, and I get the value, let us say alpha. Suppose if you measure A, and you get A plus, okay. Now I measure A immediately on this system again. Okay, now every word of this is important. So if you measure A again immediately, then what do you get? Well, you might be tempted to think that I should apply the same rule again, right? Once I have measured A, I should again write the system as some linear combination of psi plus and psi minus, and I would get either A plus or A minus, with probabilities being the corresponding squares of those coefficients. That is not true, because the word immediately is very important here. I have not given the system any time to evolve. I am measuring A, I'm getting the value A plus, and I'm measuring A immediately again. If you measure A immediately again, and if you have gotten the value A plus, you are sure to get A plus again. Okay. So what does this mean? This means that when I measure A on some system and the state of the system, and I get A plus, the state of the system after measurement of A has collapsed into the state psi plus. So this is a line that has caused a lot of discussion in the physics community and is still causing a lot of discussion in the physics community. This is the notion of collapse of a wave function. It's an active area of research. Regardless, what this tells you is the following. Suppose if I measure A on some system psi, okay, and I get A plus, what I have done to the system is basically I have made the system collapse into an eigenstate of A and corresponding to whatever value, eigenvalue I measured. So in this case, A had two eigenvalues, A plus and A minus. Corresponding to A plus was an eigenvector, eigenfunction psi plus. Corresponding to A minus was an eigenfunction psi minus. So immediately after measurement, the system collapses into the state psi plus because the experiment has told me that I have gotten the value A plus. This is called the collapse of the wave function. And this is actually a very, very important aspect. If I measure A and I measure A immediately again, I'll get the same value as I just got. Suppose if I wait and give the system time to evolve, of course, I will have to do the exact same procedure once again. I'll have to write this as a linear combination of the states and compute the probabilities. But an immediate measurement gives you the exact same value. Okay. The only way you can understand this is by saying that the state of the system immediately after measurement of the observable A has collapsed into one of the eigenstates of A. Okay. So suppose if I measure A and I get A plus, it means immediately after measurement, the system is not in state psi anymore, which is a linear combination of psi plus and psi minus. It is actually in the state psi plus. Or if I had gotten the value A minus, the system has collapsed to the state psi minus. And if I measure A once again, immediately after, I will again get the state psi minus if I had gotten this prior to the measurement. Okay. So the word immediately is very important, and this is called the collapse of the wave function. So this notion of collapse of the wave function is actually very, very important. And the goal of this short module was to introduce you to the significance of postulate 3, not only in telling you how probabilities are computed, but also in telling you how it actually affects the measurement system itself. Okay, so we will take up this notion of eigenstates and we will develop what is called the uncertainty principle in the next module by looking at computing certain quantities called variance and other things using formulas that you already know. Okay, so for now we will stop with the qualitative picture of what the postulate number 3 gives us, and we will move on to a quantitative understanding of eigenstates and the uncertainty principle in the next module.